Hello, everyone. Thank you for coming to our presentation today. I am Xichen Li. Along with my teammate Yixiang Huang, we will present our research proposal on the topic of full duplex radio frontend. This research is being conducted under the supervision of Professor Chris Rudell and Professor Wisvesh Sutton. Over the last decade, full duplex communication has evolved as one technique which potentially can address the demand for high data wireless network. However, significant barriers remain. Mainly, the radio's own transmitted signal presents itself as interference to the transceiver's receiver. We propose to introduce a new circuit and system technique which enhance self-interference suppression to enhance the data rate and spectral efficiency of current and evolving wireless applications. There are many standards which would benefit from self-interference suppression to allow simultaneously transmitting and receiving using the same frequency. Example includes car radar and neural interface, as well as sonar systems and DOCSIS 3.1 standards in cable modems. Of course, one area that can be benefited greatly from in-band full duplex communication is recently introduced the 5G standard, which demands high data rate to achieve a new level of connectivity. Using full duplex communications allows for increased spectral efficiency up to 2 times. However, achieving high self-interference cancellation has many practical implementation challenges, mainly because both the transmitter and receiver are operating simultaneously using same carrier frequency. The transmitted signal becomes a strong interferer to the receiver front end. There are three key barriers in self-interference cancellation in the analog front end. The first is a potentially long-delayed self-interference signal due to environmental reflection of distant objects. Here, you see the measured power of the reflected self-interference on the y-axis versus the round-trip time of flight or delay on the x-axis for several commonly found environments, including an office, hallway, and an atrium. The first peak is due to the short reflect, such as direct coupling between the TX and RX through the board and chip substrate, while the later peaks are attributed to environmental reflections. There have been some publications which implement integrated self-interference cancellation filters for delay below 1.5 nanoseconds. However, environmental delays above 2 nanoseconds are still large, requiring cancellation up to 50 nanoseconds delay. Self-interference cancellers with delay matching about a few nanoseconds have yet to be realized as an integrated solution in the analog portion of the radio due to the prohibitively large size of the non-on-chip components. Another two challenges are related to the high TX output power presented to the receiver input and reciprocal mixing of the self-interference and the LO phase noise, both limiting the overall cancellation. There are multiple opportunities along both the transmitter and receiver chain to realize self-interference suppression. For example, a modern Wi-Fi transceiver may require over 120 dB self-interference cancellation, and the suppression may be distributed along the receiver chain using multiple cancellation paths. Depending on the position of the canceller within the transceiver, different challenges surrounding self-interference cancellation need to be addressed. Self-interference canceller at the I front end needs to have high linearity, and baseband cancellation needs to synthesize a long delay. Besides, phase noise reciprocal mixing mitigation is required for high overall cancellation. Some prior art in the area of integrated wideband self-interference cancellation are shown here. The efforts which show promising results adopt several methods to address a different aspect of self-interference at various points in the full duplex transceivers. This method implemented the self-interference cancellation from the circuit level at the analog front-end or analog baseband, mainly dealing with the short delay self-interference. However, most efforts to date have yet to address the challenge of very high canceller linearity, reciprocal mixing suppression, and the mitigation of the long delay reflection.
Our research strengths are in the area of RF, analog, and mixed signal circuit design using standard CMOS technology to integrate the entire system on a chip. The work described in this research proposal is particularly exciting to us as it is at the heart of what we and our two advisors have worked on for several years. Building on previous 4-2-chip projects in the group, we expect to design, fabricate, and test the proposed transceiver front end within 1 year. Thank you for your attention.